taking moments about the y-axis because our moments are actually along the x direction, so we can arrive with this summation expression, no? Wherein some of the values here are considered infinitesimal of higher order, and they can be cancelled. So those which includes a a factor dy dx multiplied by more than 3, okay, are considered more than 3 times are considered infinitesimal or simply very, very negligible, such as this value here. Okay, so this can actually be neglected. Okay, and the others actually are a part of this moment, which are actually uh, considered here acting along and about the y-axis. Okay, so we consider moments mx dy, and here mx plus delta mx dy. We can assume that this value here is simply your delta mx. Okay, and here you also have a delta myx and a delta qx. Okay, so for the moments and shears, for the flexural torsional moments and shear, uh, not including of course your load q, which happens to be assumed to be negligible in that case, we come up with this equation. Okay, so in this equation we have here the flexural moment values. Okay, so this is the mx dy, and this is the uh, uh, mx, okay, dy plus delta mx dy. So where is that? So we have here your partial derivative, okay, this one here, okay, and also your myx dx plus the partial derivative of myx plus delta myx. Okay, so this is now your value here. Okay, so myx ddx plus this to 1 and this one here. Okay, and of course your qx and uh, delta qx. The other qx is actually acting along along the or crossing this axis, so this will actually be 0. So what will be the moment arm of your qx plus delta qx? So the moment arm will simply be a dx there. So again, you will be having a triple product of dx, dx, and dy, making it also negligible in that case. Hence, this here, this part here, when I multiply it, will yield, okay, so this will yield to be a triple product and considered to be an infinitesimal of higher order. So we can actually also consider this to be 0. So what remains are this, which can actually cancel out. So this will cancel with this one here. We can also cancel this and this. So what remains are 1, okay, 2, and 3 values. But there is a dy, dy, and a dy there. So we can cancel the dy's. Okay, such that what remains now is simply this is no longer considered because it already canceled out a while ago. So these are now the remaining, okay, expression that we have. Also this one. And the last is this one with a dx there, okay? So with the dx here. So these are the three remaining. And this is a positive, positive, and negative, but the dx will also cancel out such that this equation now will represent your equation 1. And similarly, considering the other side or the other summation series, which is summation moment about the x equals 0. Of course, the orientation and the description of the variables concerned will just what? Will just interchange. Okay, but still, you will have to note that you have a flexural, torsional, and a shear. Flexural in y, torsional in xy, and a shear. Okay, so these are now equations 1 and equations 2 to be combined, no? In such a way that if we take the summation of forces vertical equals 0, we simply add all the shear. So this is your delta qx, delta qy, and the load. Okay, so simply this is the change qx. This is the delta qy, and this is the load. Okay, so what about the qx and the qy? They will actually be canceling each other because of the qx plus delta x, the qy plus delta y. Okay, so for your third equation now, we simply cancel the dx dy here, and you get a simple equation, which is equation 3, upon which your equation 1 and 2 will be plugged in this equation, yielding to the fourth equation, which is simply um, the derivative of qx with respect to x, if we uh, will substitute the value, okay, of q here in this equation, so it will yield this equation here. Okay. Okay, so qx is simply the derivative of mx plus the derivative of myx. Okay, so you just plug it in here such that your ddx becomes the derivative of mx with respect to plus the derivative of myx with respect to y. Okay, plus the dy of the derivative of my all over dy plus the derivative of mxy all over dx. And then, if we expand this out, we will form now an equation similar to this. Okay, so this will become the second derivative, and this also a second derivative there. Okay, so this is second derivative. Okay, so correction. And then these two will actually form a sum of the derivative, the second derivative of myx with respect to dx dy. So this is dx dy. Okay, so twice, because this also myx and mxy are just the same. Take note that mmxy and myx are just equal in magnitude. And of course, your q here will be transposed at the other side to get your differential equation, which can be further simplified into this equation by simply applying, no, or converting the moment in the moment variable to a load variable there. We all know that the moment is simply equivalent to the derivative of the load. Okay, the derivative of the load. In equation, the previous equation here. Okay, so the moment is simply equivalent to the second derivative of the load. With, of course, what's this? This is simply a property, no? Has something to do with the modulus of elasticity and the Poisson's ratio. So this is now your uh, uh, flexural property D, okay, which includes, of course, the moment of inertia here. This is a moment of inertia, I. So you can call this a flexural property or simply a flexural rigidity if I is included. Okay, so this is simply an EI term there. Okay, so this has something to do with an EI term with, of course, we are talking of three-dimensional coordinates. This is given to be a matrix property. And finally, we take note that this two-dimensional, okay, so this is a two-dimensional equation, differential equation, has some similarities on a one-dimensional equation, which is a beam. So from a plate, we now converted it into a beam, no? In terms of, okay, so this is an EI. This is now our equation of comparison from a plate to a beam. So this is EI, D, and then D to the fourth with respect to dx to the fourth of your load is equal to qx. So since this is only one-dimensional, you only have one variable of differentiation. Here you have two variables of differentiation. Okay, so take note of the correction there. And the rest here are simply the differential equation in terms of shear, moment, slope, and deflections in which we have studied in our mechanics of materials. Thank you very much, and I'll see you on the next video for the continuation of the principles on buckling of uniformly compressed plates. Thank you for listening.